All right, so I want to walk through the solutions for the Assessment 7 review. The first one is a MATLABable problem. You create the y column vector with the y components 1, 3, 2, 4, 4. You create the x vector where you have the ones in the first column, and then the x values 2, 3, 4, 5, 6 in the second column. You have MATLAB calculate the vector x transpose x inverse times x transpose y. That comes out as the vector 0, 7 tenths. So the regression equation is going to be y is equal to 7 tenths x. And that's it for problem number 1. All right, so in problem number 2, you have u is the vector 1, -1, 2. V is the vector 2, 3, 1. We're using u dot v here, so it's pretty straightforward. The norm of u is going to be square root of 1 squared plus -1 squared plus 2 squared, which that's 1 plus 1 plus 4, which gives me the square root of 6. Magnitude of v is going to be square root of 2 squared plus 3 squared plus 1 squared, which is 4 plus 9 plus 1, which is the square root of 14. U dot v is 1 times 2 is 2, -1 times 3 is -3, 2 times 1 is 2, so this is going to be just 1. The distance from u to v is the magnitude of u minus v, which is the magnitude of, let's see, 1 minus 2 is -1, -4, 1, which is square root of -1 squared plus -4 squared plus 1 squared, which is square root of 1 plus 16 plus 1, which would be the square root of 18, which would be 3 radical 2. And then the projection of u onto v is uv over vv times v. U dot v we just discovered was 1. V dot v is magnitude of v squared, so that's going to be 14. The v vector is 2, 3, 1. So we're going to get 1/7, 3/14, 1/14 should be the resulting projection. All right, so let's move on to number 3. 3 is a verification of the triangle inequality. U here is 2, -½ 1. V here is 3/2, 2, -1. So magnitude of u is going to be, all right, so but we have this different inner product, right? So the inner product here is u1 v1 plus 2 u2 v2 plus 3 u3 v3. So u1, so we take square root, u1 v1 is just going to be 3. Oh, we're just doing u. Sorry, this is u. So this is going to be 2 squared is 4. -½ squared is 1/4 times 2 is 1/2. And then 1 times 1 is 1 times 3 is 3. So let's see, that's 7, 14 over 2 plus 1 over 2 is square root of 15 over 2. Which I think when we put that in the calculator comes out as approximately 2.7386. Magnitude of v is going to be 9/4 2 times 2 is 4, times 2 is 8, and then 3, right? So let's see, this is 8, 9, 10, 11 over 4 is 44, and 9 is 53 over 4, which when you throw that in the calculator, you get approximately 3.6401. Magnitude of u plus the magnitude of v then is approximately 6.3787. So now we need the magnitude of u plus v, which is the magnitude of, let's see, 2 plus 3 halves is 7 halves. That's 3 halves. And 0. So we get a break with the 0, right? So this is going to be square root 49 over 4 plus, let's see, it's 9 over 4, 18 over 4 plus 0 gives me square root of 67 over 4, which is approximately 4.0927. This is less than this, so this implies that, sorry, not that, this is less than this, there we go, which implies that u plus v norm is less than or equal to the norm of u plus the norm of v, so the triangle inequality holds with this inner product for these two vectors. All right, so let's look at problem number 4. So 4 gives me u is 4, 1, negative 5. V is 2, negative 3, 1. We want to show Pythagorean theorem with a typical dot product here. So u dot v is going to be 8 minus 3 minus 5, which is 0. So we've shown that u is orthogonal to v. So that's good. All right, so now we have to show the Pythagorean theorem. So let's take magnitude of u squared is going to be 16 plus 1 plus 25, which is 42. Magnitude of v squared is going to be 4 plus 9 plus 1 is 14. So the magnitude of u squared plus the magnitude of v squared comes out as 56. So now let's look at what is magnitude of u plus v squared. So this is the magnitude of 6 minus 2 minus 4 squared. So it's going to be 36 plus 4 plus 16, which is, lo and behold, 56. These are equal. So u plus v squared is equal to u squared plus magnitude of v squared, which is the Pythagorean theorem holding for these two vectors in R3 under the standard inner product. All right, so let's move on to number 5. All right, so in problem number 5, we're using the standard inner product for continuous functions from -1 to 1 to show orthogonality. So the inner product here is going to be an integral from -1 to 1 of the product of the two functions. It's 1 plus x squared times 2x times the square root of 1 plus x squared dx. So this is just the integral from -1 to 1 of 2x times 1 plus x squared dx, which is the integral from -1 to 1 of 2x plus 2x cubed dx. So this is going to become x squared plus 2/4. So that's just going to be a half x to the 4th from -1 to 1, which is 1 plus a half minus 1. Oh, wow. These are all negatives. That's negative, that's negative, that's negative. This is negative. This is negative. So this is negative minus a half. So this is a half minus a half, which is 0, which gets me orthogonality. All right. So that's number 5. Let's move on to number 6. 6 is literally a MATLAB problem. You're going to make the vector v by putting in 0, 0, 2, 0, 1, 1, 1, 1, 1. You're going to Graham-Schmidt vector v, and that's going to return 0, 0, 1, 0, 1, 0, 1, 0, 0, which is literally the standard basis. So Graham-Schmidt in this case returns the standard basis. All right, so that's end of problem 6. Let's look at problem 7. All right, so the first thing we have to note is that the dimension of R3 is 3, and the size of set S is also 3. So we have right size here. So now we just have to show orthogonality, and we have to show normality. All right, so orthogonality is 1 over root 2 times 1 over root 2, 0 dot negative root 2 over 6, root 2 over 6, 2 root 2 over 6. So this times this is going to be negative 1/6. Times this is 1/6, and then 0 makes that 0, so that's good. 1 root 2, 1 root 2, 0 by the other vector, which is 2/3, negative 2/3, 1/3. So this is going to become 2 over 3 root 2 minus 2 over 3 root 2 plus 0 is 0, so that's good. Negative root 2 over 6, root 2 over 6, 2 root 2 over 3 dot 2/3, negative 2/3, 1/3, positive, right? That's a positive 1/3. So this is going to be, let's see, negative root 2 over 9. Same here as negative root 2 over 9. This one becomes 2 root 2 over 9, which is 0. So we have orthogonality. So now we have to play for normality. So we take the norm of 1 root 2, 1 root 2, 0, which is going to be a half plus 0, which is the square root of 1, which is 1. All right, so now we go negative root 2 over 6, root 2 over 6, and 2 root 2 over 3. So this is going to give me 2 over 36, which is 1 over 18. This one also is 1 over 18. And this one becomes, let's see, that's 4 times 2 is 8 over 9. 8 over 9. 8 over 9 is 16 over 18, 17, 18 over 18. So this is the square root of 1, which is 1. That's good. And then the last one, 2/3, negative 2/3, 1/3 gives me 4/9 plus 4/9 plus 1/9 is 9/9, which is 1. All right, so we have both orthogonality, we have normalcy, and we have that it's the right dimension. So this is, so S is orthonormal basis for R3. Okay, so let's move on to the next problem. All right, so this is asking, is S orthogonal, is it orthonormal, or neither? So let's start testing orthogonal. 2, -4, 2 dot 0, 2, 4 comes out as 0, -8, 8, which is 0. 2, -4, 2 dot -10, -4, 2 is -20 plus 16 plus 4 is 0. And 0 to 4 dot -10, -4, 2 is 0 minus 8 plus 8, which is 0. So we are orthogonal. Orthonormal is going to blow up really fast. If we take the magnitude of 2, -4, 2 with the standard dot product, we're going to get square root of 4 plus 16 plus 4, which is the square root of 24, which is not 1. So we are not orthonormal. All right, so there's your solutions for your review. I hope it's making sense. If you have questions, do the drop-in or send me an email, and I'd be glad to help. I hope you're all well. Hope to talk to you soon. All right, bye-bye.